when we had previously discussed motional electromotive forces, there was this interesting mathematical step that we had made using the triple vector product. And there were three equivalent forms for the motional EMF. And I thought it would be interesting to see what each form teaches us. One form is just how we calculate the EMF. We would then transform it into something that related it to the changing magnetic flux. It'd be interesting to explore the final potential remaining form. So let's take a look once again at how we had set this kind of a thing up. So the idea is I'm going to have, just as I had in the previous diagram, I'm going to have a minus terminal and a plus terminal, and I'm going to have some external resistance that's going to be connected to these terminals. And I'm then expecting, here's my resistance R, I will be driving some current I through this system from the plus through down to the minus terminals. But then the way the EMF gets generated between these plus and minus terminals is that I'm going to have then some kind of a wire loop, like so, that's then moving through some magnetic field and experiencing, therefore, some kind of changing magnetic flux. Now, our underlying theorem told us that the motional EMF in this situation, basically what amounts to the voltage that we would associate with these plus and minus terminals, is the integral from A to B. And normally we would write the voltage as I'll write it as minus that integral of the electric field now that this wire feels, the electric field inside of this conductor. And we know that for a conductor moving through a magnetic field, that electric field that gets generated inside is minus V cross B. And then, of course, that has to be integrated dl in order to give us the motional EMF. These minus signs here, of course, cancel for us. And we have now, once again, the issue of this triple product. Now, I wanted to rearrange that triple product. As you remember, we can use the cyclic property of the triple product. There are three equivalent ways to write it. We had looked at the form in which we had looked at the form in which we generated a change in area by getting dl cross V. I want to try the other form. So to obtain that, what I have to do is I actually have to cyclically rotate things the other way. I'm going to move everything backwards down the row. So B is going to move into the place of V. So I'll have B cross. dl then is going to move backwards into the place of B, dl. And then V, which is out here, is going to have to pop out actually backwards. It's going to move down the row and end up out in front, dot V. So this is just a mathematical identity on the triple product that we have. What's going to be interesting is how we can interpret this physically. Now, if I think of this physically for a moment, this term, B cross dl, this should look fairly familiar to us, actually. Right? We can turn this into, of course, it should look very familiar to us. It looks almost like the force law on a chunk of wire. Here, let me divide by I to try to make this a little more clear. If I divide by I on the outside and multiply by I back on the inside, this would be B cross I dl. It looks almost like the force on a segment, dotted with V, right? IDL is normally how we compute the force on each of our wire segments. The problem is, though, the cross product is in the wrong order. So I had better then pull out a minus sign. So I'm going to have minus 1 over I, the integral all the way around my loop of IDL cross B dotted with V. Now let's take a look at what this means. Let me take a little segment here of my loop. So here's a little chunk of my loop, a little dl, as I integrate around my loop like so, right? And now that dl is moving around in the magnetic field as this loop is changing, its shape and moving around, different portions of it moving in different directions. And this thing might be moving, say, off in a direction like this, v. And what I have here then is this is the force on my little chunk as it moves, dotted with its velocity. Well, that force dot velocity is a famous factor. If you think about it, force times velocity is equal to, well, that's force times velocity is distance over time. But force times distance we know is work per unit time, and work per unit time we know is power. So this is just the force from the field dotted with the velocity. This is some kind of power. The only mysterious part is the fact that I have this minus sign. But if we think about this carefully, this is the force that the wire is feeling due to the fields. We are the ones who are pushing the wire through that system, right? Minus that force is the force that we have to put on the wire in order for it to move. So let me pull in that minus sign and change this into the force due to us. So what we have is 1 over I. The minus sign comes inside because now we're talking about the force that we have to apply in order to move the wire the way it's moving, because we have to counter the external forces on it, dotted with the velocity of the wire. But this is just the power that we are putting into the system. So that is power, mechanical power we are putting into the system. And when on each little segment, and of course when we add them all up, that just gives us the total power that we are putting in. So we have this final interesting relationship that the motional EMF is equal to 1 over the current times the power that we are putting into the system. Or, of course, we can turn this around a little bit. I'll probably write it over here closer to the diagram, that the mechanical power that we are putting into this system equals actually the motional EMF of the system times the current I. But this gives us a beautiful expression of conservation of energy, because the EMF times I, that is the electrical power that's being pumped through that resistor.